I think we can start, and it's a great pleasure for me to welcome all of you on behalf of all the department. My name is Sandro Zampieri. I'm the director of the Department of Information Engineering that is hosting this distinguished lecture of today. Let me say that this is the second distinguished lecture that we are proposing this year, and the first one has been proposed 1 month ago. It was about big data, and this is about quantum revolution, and so what quantum mechanics could cause in the future as a revolution in information technology. The next one will be about neuroscience. So it's this series that we are proposing every year is about these general subjects that is not related or strictly related to the topic of our department, that is information engineering, but it tries to go over and to expand the interest of our department also outside our classical subjects. Today we are proposing this possible interaction with the physics and with the quantum mechanics in particular. So for me it's a great pleasure to have so many people today attending this lecture. And now there will be my colleague Paolo Villoresi that will introduce our distinguished lecture of today. Okay, thank you.
Thank you, Sandro. Good morning, everyone. Our gathering today deviates a bit from the traditional solo talk. Having a program in which we have indeed a part in which Professor Lloyd will speak alone, and then a dialogue with our colleague Gianfranco Bilardi about the impact of quantum technology on aspect of the information in general. So there are different directions that are expanding, evolving these years, and so we try to look into a few of them. Okay. So our distinguished speaker, Professor Seth Lloyd, has a career in physics. He started with the master in Harvard, and so for the AB degree in physics in Harvard University, his master of advanced study in mathematics, and master of philosophy in history and philosophy of science from Cambridge University, and finally his PhD in physics from Rockefeller University. After postdoctoral fellowship at Caltech in Los Alamos, he joined the MIT faculty in 1994. He is presently Nam P. Su Professor of Mechanical Engineering and Professor of Physics at MIT. So I would say that it's not difficult to describe the contribution of Professor Lloyd to the quantum information science. Indeed, he contributed to all aspects of this science, starting with a seminal work on how a quantum computer may be designed, with a theoretical illuminating paper that appeared in this illustrated weekly magazine Science in 1993, and then was followed after a few years with an experimental realization in California first, and then in Europe in Delft, in terms of the Joshua algorithm realized in superconducting system, and this spurred the race now to find the most suitable technology that will realize the quantum computation and that will prove this quantum supremacy in this aspect. Okay. Besides this, introduced the field of quantum metrology. So how you can go beyond the limit that the classical statistics is imposing when you're doing measurements. And this is in a long series of contribution that were done also together with the Italian scientists like Lorenzo Maccone and Vittorio Giovannetti, that say show how you can say beat this say limits that say scale the error with the square root of the number of measurements, and then can get close to the quantum limit, which scale inverse to the number of tests. Okay. And then he addressed the problem of finding the role of coherence or quantum coherence in biological systems. That is a very fascinating subject, and that attract the interest now also a wider community, including biologists and scientists that study and investigate the role of genetics and say the functioning of brain. And we're very glad to welcome our friends from the biology departments working on this. Also on protocols that quantum information can contribute to secure communication, as the say recent work on quantum data locking that show an exponential advantage in say doing locking of data, so in securing the communication when you have qubits instead of bits. Okay, and these are a few of the topics that Professor Lloyd contributed, and finally investigate a very basic aspect, the fact that interaction are the most fundamental thing, and you can think of the universe as then as gates, and you can calculate how many bits there are around, how fast they can run, okay, using fundamental theorems on this, and then the capacity of the universe in terms of a computer that continuously elaborates its own future. Okay, and for these reasons, we're extremely happy to welcome here Professor Lloyd, and please join me saying welcome and giving him hands for starting his talk.
Thank you very much. I think I'm okay. Thank you very much, Paolo. It is a great pleasure to be here in Padova. I've never been here before, and we have been wandering around the city, going to many, many churches and museums, and eating lots of fantastic food and drinking lots of very refreshing spritzes, and this is, I have to say, it is a wonderful place. And I'm looking forward this afternoon to talking, let's see if we can actually get this back here. I'm looking forward to talking with students and other faculty here, whoops, and who are about actually doing science. I thought that I would talk today about, Paolo asked me to talk about the fundamental role of quantum mechanics in the universe in terms of information. And so I put on a subtitle, which is, it sounds quite relevant since you already had a talk a few months ago about big data. This talk will be about big quantum data. There are a couple of reasons for doing this. One is that quantum mechanics makes nature discrete and digital. So quantum mechanics is responsible for the digital nature of the universe. Another reason is that quantum mechanics can really help us in terms of gathering information in the universe and processing that information. And the third reason is that you know probably that there's only two ways to get grants for doing research these days. One is to have big data in your title, and the other is to have the word graphene in your title. So we can merge this to say, you know, graphene-based quantum random access memories for the analysis of big data, and then we're absolutely sure to get the grant. So it's going to be great. So speaking of which, how many people here have a background in quantum mechanics or who have studied quantum mechanics? Okay, lots of people. And how many people here do not have a background in quantum mechanics and haven't studied quantum mechanics? Right, and how many people didn't raise their hand for either question? That's right, the truly quantum mechanical people in the audience. They both have and haven't studied quantum mechanics. Okay, so it's no secret that our society is awash in data. We have Avogadro's number. 6 times 10 to the 23, it's the number of hydrogen molecules in a gram. It's the number of bits of information generated by the human species in a year. So if you look at the total amount of information that's whizzing back and forth on the internet, and you accumulate it over a year, that's about Avogadro's numbers of bits. Which puts in perspective, first of all, that the amount of information we're generating is very large, compared with, for example, the amount of information that's written down in books, which is something more like probably 10 to the 12th bits in total. But it's also very small, because hey, it's just a gram of hydrogen molecules, you know? It's like, that's not a lot in terms of actual physical matter. So we are in a realm of big data, but it's not, we have a long way in which we could go. And in fact, this whole business about big data, which may I say, I'm sure that because you guys are information sciences department, probably you get quite tired of hearing about big data too. The point is that it's not necessarily good to have this amount of data. Most of this data is complete junk, all right? And our role in this is to figure out ways to get the information we need from this. Actually, my friend Katie and I were discussing this along the way because we were seeing so many wonderful, wonderful frescoes from the Trecento here. And we were thinking, this is not the first time that a human species has found themselves in this kind of problem of dealing with lots of data. The beginning of the Renaissance was a time when a huge amount of new information was coming in. When Dante said, "Nel mezzo del cammin di nostra vita mi ritrovai per una selva scura che la dritta via era smarrita," part of what he was responding to was the fact that things were changing very rapidly, and they were changing rapidly because all kinds of new information was coming in, actually largely from the Arab world, which had preserved not only ancient Greek texts, but had introduced a lot of their own mathematics and Babylonian mathematics, and this all got introduced into the European system, and the amount of information that was available expanded by orders of magnitude, and people responded by being confused, which is the right response to new information, and then coming up with absolutely amazing responses. Actually, Padova is, just looking at the Cappella di Scorvelli, and the Battistery, and the amazing, and the murals in the frescoes in the Basilica de San Antonio. The response to this kind of new way of thinking was unbelievable. And tremendously creative. I don't know if in our world of apps we're being that creative yet. Actually, in point of fact, apps can only solve a certain set of your problems. For instance, if you live in the third world and what you really need is a sewer system, an app won't help. I mean, you could have an app that tells you which field to go to the bathroom if you don't have a sewer system. But what you really need is a sewer system. I would give this app its name, but this is being recorded, so I'm not allowed to tell you what the name of this particular app is called, but I think you can guess it. So, this number, which has, by the way, this number of Avogadro's number. So actually, a few years ago, it was a lot smaller than, let me see if I can actually find the laser pointer here. So a few years ago, I did this calculation, and it was 10 to the 18th. And a few years before that, it was 10 to the 15th. This is a number that's been growing very rapidly. And if you extrapolate backwards, there was a time, which many people in this room remember, which was a mere 15 or 20 years ago, when actually if you wanted to go find things, you had to go to the library and look around for them and read books and then have serendipity guide you to new ideas. And so a very funny thing has happened to the human species in the last 2 decades, which is that we went from being hunter-gatherers of information, cacciatori e raccoglitori. By the way, I want to point out, perhaps people don't, because I haven't been anatomically correct here, I want to point out that it is the man with the beard who is gathering little fruit-like bits of information from a tree, and it's the woman with the long hair who is spearing a bit of information with her spear. I want to point out that I'm being politically correct in case you didn't notice that this is a man and this is a woman. For thousands of years, indeed since the entire existence of the human species, our relationship to knowledge has been one of being hunters and gatherers, cacciatori, raccogliatori, tore, because information was very hard to find, and useful information was very hard to find. Actually, again, I have to mention the history of this one city, Padova, because after it was this university was founded by people who didn't like the University of Bologna, they came here and they founded a university where they wanted to study new things and created a university studying all kinds of things like medicine, practice of medicine that were not being studied in Bologna. And as a result, people from all over Europe came here. I mean, during the 1400s, 1300s, 1400s, 1500s, this was in some sense the premier university in Europe for people to come to study things which we think of now as being related to science. And they would come for years and years and years. Then they would get their laurea. We've seen lots of those around, some on sober people and some on less sober people. And they, this was the place to come. So people would come here to talk with the people who knew what was going on, to learn from them, to discuss what was happening, and then they would go back, and so the University of Padova had a great role in the creation of knowledge during the Renaissance and before in the pre-Enlightenment era. And so, this was the normal way to do things, actually, until a few years ago. And actually, I claim that this still is the right way to do things. You may notice that I'm standing here in front of you as a person, as a human being. We have been, Paolo, Gianfranco, we've been discussing, sitting together, having a very nice meal, talking about ideas about science. I actually believe that this is the way to go. In fact, you may have noticed that my PowerPoint slides here, my relationship to PowerPoint, well, I have no relationship to PowerPoint because I've never made a PowerPoint slide. I actually believe that PowerPoint is a tool of Satan. Okay? It is a tool of the devil. If Giotto knew about PowerPoint, then in his beautiful frescoes, PowerPoint would be one of the things going into Satan's mouth and then coming out the other end. It is a tool made for businessmen to convince other businessmen of things that are not true. Hence, it is very appropriate to use in scientific settings. Anyway, what's happened is, we as human beings, as a species, have always been hunter-gatherers of information. And something rather sad happened over the last 2 decades, which is we became instead filter feeders of information. That is, like oysters and baleen whales, that now we're just being overwhelmed by vast quantities of information coming in all the time. And our goal is to actually somehow get a few little bits that are useful. So, here's this, these are animals, the ostraca, the balena. They have all this information that's coming in, and then they have various methods for trying to get a few tiny little bits of useful information out. I mean, somehow I think that, hunter-gatherers, oysters, which is more noble? Well, oysters are noble, but still. Okay, so how can quantum mechanics help us in dealing with this. First of all, let's just talk about what information is. So information, one of the great features of information, and this is really an amazing discovery, is that you can measure information. So the measure of information is well known to be a bit. It's the simplest possible measure. There's a distinction between 0 and 1, yes or no, true and false, a distinction between any two possibilities. And there was an amazing discovery, which was really made in the middle of the 19th century. Probably the name of Claude Shannon is the one most closely associated to this, is that you can measure information in terms of bits, and that the amount of information is independent of meaning. That is that, you know, if the person bringing a cable to your house so that you can watch television, their job is to ensure that you get 20 megabits per second, and it doesn't matter if you're watching Puccini or if you're watching porn, right? It's not their job to worry about it. It's just getting the number of bits in there. Now, the other feature about information that is extremely important, and this is to move towards the quantum mechanical piece of information, is that information is also physical. That is that whenever we have information that is registered or stored, then it's registered or stored or represented in a physical system. Information is physical was the slogan of Rolf Landauer, who was a researcher at IBM, who, starting in 1960, came up with some of the earliest results in showing how you could represent information at the level of elementary particles, such as electrons. And here, for example, we could have an electron over here could represent a 0. Electron over there could represent a 1, because all we need to represent a bit of information is some physical system that has two possible states. And then if we want to have information processing, so if we want to flip a bit, we move the electron from over here to over there, so the state 0 becomes a 1. So we can register information by the different states of matter, and then we can process information, flip bits, by introducing dynamics that transforms those states of matter. And here I've actually, of course, this is exactly, when you have lots of electrons, this is exactly how information is stored on a computer like this one. You know, a 0 is stored by having a whole bunch of electrons over here, capacitor uncharged. A 1 is stored by having a whole bunch of electrons over here, capacitor is charged. And if I want to change a 0 to a 1, I simply charge up the capacitor. At the level of a single electron, we can imagine a single electron capacitor, which is really just an atom. Atom in ground state with at lowest energy state is 0. Atom in excited state is 1. And to move it from the ground state to the excited state, we simply take the electron from one state to another. Now, here's where quantum mechanics comes into a role. So in quantum mechanics, in order to describe the actual behavior of real electrons, we need to use quantum mechanics. And the central feature of quantum mechanics, for those of the people who studied it already, who know this, for people who didn't study this, you might already have heard of this, is what's called wave-particle duality. And it means that the electron over here, so the electron is a particle, but it has a wave that's associated with it. And the wave, in some sense, tells you the probability of finding the electron in a particular spot. More precisely, actually, the wave is a complex numbered valued wave. The square of its amplitude tells you the probability. But the basic point is where the wave is big, you have a high probability of finding the electron. So here's a wave that corresponds to the electron over here. Here's another wave that corresponds to the electron over there. We call this 0. We call this 1. But the funny feature about quantum mechanics is that these waves can add up. They're like water waves or like sound waves. And I can put two water waves coming in from one side of the bathtub to the other. With my daughters are now 19 and 21, actually. And but when they were 3 and 5, you put them both in the bathtub, and they send a wave going from one side to the other, and the waves meet in the middle. And where they meet, they add up, and they splash out. So the waves in quantum mechanics, these quantum mechanical waves, add up as well, and that means that I can add this wave to that wave to get a wave for a single electron. It looks kind of like this, and this is a wave for one electron, and because the wave tells you roughly where the electron is, this tells you the electron is both here and there at the same time, in some funny quantum mechanical sense that nobody really understands, including me, and I spend my life working on this stuff. Our intuitions, our feeble classical intuitions don't allow us to comprehend this because we don't run into this on an ordinary basis, unless maybe we're watching Lionel Messi with a soccer ball. Doesn't appear to be here and there at the same time. By the way, I felt that it was really cruel that Italy got knocked out of the European Cup when it was such a great team. I had really high hopes. Anyway, but I'm told I don't have enough time to talk about this. Okay. So this is a quantum bit, or a qubit, as it's called. The electron can be here and there at the same time, which means that the bit that's registered by the electron, in some funny sense, registers 0 and 1 at the same time. In some funny, strange, counterintuitive quantum mechanical sense that we don't understand intuitively, but we do understand it mathematically. So we can use the ordinary mathematics of quantum mechanics to describe what's going on. It works. Strange and counterintuitive things happen, but it works. Now, let's look at what this means for the universe as a whole. I know this talk is very cosmic, so this is my cosmic slide. I better explain this. So this is like a star. This is like the sun. These are stars. This is a planet. This is a comet, just in case you couldn't tell. Quantum mechanics, the role of quantum mechanics, you could say, is to make the universe digital. Quantum mechanics, the quantum in quantum mechanics makes things discrete. Energy comes in chunks. So the converse of wave-particle duality is that light, which we think of as being a wave, classically is actually made of particles called photons. It comes in chunks. These chunks make the universe effectively digital. And every elementary particle, every atom, every molecule carries with it bits of information. So we can store bits of information on electrons. We can store bits of information on photons. This is a picture, if you like, of a molecule. You could think of these as an organic molecule. These are carbon-13s. And the nuclear spins, we say spin up is 0, spin down is 1. So any quantized degree of freedom carries information with it. This, by the way, is something I realized while I was working to build quantum computers, where we said, oh, we'll start with maybe with atoms or maybe with light. And they said, well, we can have anything we want. And so when these particles move and interact, so for instance, the electron moves from here to there, the bits flip. Or if I have two particles and they carry spin with them, so one has spin 0, other spin up, other spin 1, they bounce off of each other, they collide, and then the bits flip. So this means that everything in the universe registers information. Every interaction between elementary particles, atoms, molecules, etc., processes that information, which means in some actually strict mathematical sense, the universe computes. The universe is computing. And in fact, this means that we are not, even though, we're going through a hard time right now trying to extract information from the world. By the way, I'm sure you can tell that these are smartphones right here. They're typical for when these people are wandering around about to run into something. We're not actually the first beings to try to extract meaningful information from a sea of bits. That everything out there in the universe, the light that's coming in from the sun, contains with it information, potentially useful information. More than 1 billion years ago, something happened and life began. So we have organisms that are actually extracting this useful information from the light from the sun. Somehow they figured this out. By the way, it's incredibly ironic that we know much more about the origin of the universe than we know about the origin of life. Strange. But since I don't have time, I won't talk about that more. Life itself, actually, is all about extracting meaningful information. The ultimate big data is all the data, the information that's out there, the light coming in from the sun, the heat coming from hot water vents at the bottom of the ocean, the information that caused stars to form in the first place, and galaxies and planets. That's the real big data that's out there. And somewhere along the way, something, our distant living ancestors figured out how to deal with this ultimate universal big data. And I'm sure you can, now that you're used to my incredibly expressive PowerPoint slides, you realize this, of course, is DNA. This is a cell. Here's the cell membrane. These are, are receptors on the cell membrane where molecules are being taken in from the outside. These are molecules carrying information that could be used, but unless the DNA can produce enzymes that allow the cell to process that information, then it can't be used. So if you think of, a human being trying to find a new way to use their smartphone, the ultimate way of doing this is a cell mutates to be able to form an enzyme that suddenly allows it to process a form of food that's out there that wasn't there before. That's real information processing. So just to summarize, the universe is about information. That information, the reason that the universe is about information, about digital information, comes from quantum mechanics. Quantum mechanics makes everything discrete. Quantum mechanics is weird and strange. So quantum mechanics has these funny features that bits can be in two places at once. Quantum computers are devices that, if you look here's a quantum computer with its quantum bits being in little waves being in two places at once. This is, by the way, what the computers that I learned to program when I was in high school looked like. They, had little tape drives and things like that. You had to switch individual switches on the front of the computer to enter in information. So human life, and life has always been, it's an exercise in machine learning. It's an exercise in processing data. And quantum computers, by the way, I will make an advertisement here for our recent work. Quantum computers turn out to be excellent. One of the things that they're really excellent at is processing data and doing machine learning. Many of the common algorithms for doing machine learning, such as cluster finding algorithms, deep learning algorithms. By the way, does anybody here work on deep learning? Right. Yeah. So yes, I have to tell you that a few years ago, when we started trying to quantize deep learning to work on deep quantum learning, my postdoc came in and said, "Oh, let's work on deep learning," and I got really excited. Oh, computers are going to tell us all kinds of deep things about the universe, truth and life and love and happiness. But it turned out they were just deep neural networks. It's okay. So yeah, the universe is about information. It's been processing information ever since it began. This information is digital because of quantum mechanics. Quantum mechanics has all kinds of strange features about it, which allow information to be processed in ways that it can't be processed classically. The origins of life are actually an exercise, if you like, in machine learning. Of course, they didn't describe it that way back then. But it's an exercise where a physical system learns how to take advantage of the information that's out there. We human beings have reinvented ourselves over and over again to take advantage of the information that's out there. And now we're actually building very powerful classical computers and even and potentially very powerful quantum computers to take advantage of this information. It's not a new renaissance yet, but maybe if we work hard together, we can make that happen. So, thank you. Thank you very much.
Okay, so a few weeks ago, 2-3 weeks ago, Paolo contacted me and said, well, we have the great pleasure of having Seth Lloyd giving the next distinguished lecture in the department, but I decided to try a new format and reducing the time of the speaker at first, but then supplementing with some kind of dialogue, and asked me to be part of this dialogue. So we'll try this experiment. I don't know exactly how it will go. It's quantum uncertainty again. So at first I started asking myself, how can I make sure to bring up topics for discussion that are relevant to Seth's work. And then I discovered that the real question was, how could I possibly come up with some topic that is not relevant? Because Seth has really covered many, many different issues. And we definitely don't have the time to touch even a small fraction. But I will start with trying to probe a bit deeper in something that Seth has already said today. So that quantum physics has showed us that the world is digital. To some extent, we thought before that the world might be analog, but we found ways since the diode and so forth, and then with the transistor, to interact with the world in a digital way. But I think what Seth means is that now if we really look down deep at the most basic level, the world is physically digital, and physics is as much information as it is energy. So of course, for our department, this is very good news. Okay, so I'm going to ask a question to hear Seth's point of view. Let me pretend not to agree with the fact that the world is digital, because after all, in the description of reality by quantum computing, we use wave functions, and the wave function, even for a qubit, is a linear combination of the 0 state and the 1 state by two complex numbers. So, two questions. Why do we call that 1 bit? We are assuming there is an underlying reality modeled by the wave function where there is more than 1 bit. And if those complex numbers can somehow be represented by bits, how do we guarantee that a number of bits, a finite number of bits, is sufficient? In other words, ultimately the information in the universe is finite as opposed to be infinite. Of course, we know that for many centuries the main mathematics in physics has been the mathematics of continuum, so a real number by itself contains infinitely many bits, but the question is, do they really have physical meaning, or are just there, most of those bits are there for mathematical convenience? But unless we can say, I guess, they are there only for mathematical convenience, we have not reached the conclusion that the universe is finite. And since Seth has even computed the number of bits in the universe, which I think are supposed to be about 10 to the 92, he must have an answer to this question.
Yes. Well, I actually think is this working? Yeah. Okay. So let's not set up a feedback loop, a destructive feedback loop. Maybe we can have constructive feedback. Yes. So what you say is quite right, and indeed, quantum mechanics does have this sort of wave-like feature, right? And these waves are continuous, and so there is a sense in which these waves could contain an infinite amount of information. But it's important to remember what the definition of a bit is. A bit is something that has two distinct possible states, 0 and 1, or capacitor charged or uncharged. And if I have an electron that could be here or there, so for instance, atom in its ground state and atom in its excited state, then these states are distinguishable from each other, electron here or electron there. Now there's a continuous infinity of other wave-like states that are not reliably distinguishable from each other. So if you wish to use this electron to store a bit of classical information, yes or no, then it stores just 1 bit, even though the wave that describes it could require an infinite number of bits to describe. So in terms of actually registering information, the electron stores a bit. It's useful actually to remember where information theory comes from, the mathematics, it was actually, as information theory was first proposed by Claude Shannon in the 1940s, but the basic formulae of information theory were developed in the latter part of the 19th century, in the 1800s, by people like Boltzmann, Maxwell, and Gibbs, who were trying to come up with formulas to describe the quantity entropy. And in retrospect, what they discovered was that entropy is in fact bits of information. It's a finite number of bits of information that are required to describe a particular physical system. So if you actually are looking at the number of bits that are actually registered by things in the universe, that is finite, even though, as you say, completely correctly, that this kind of continuum of waves has an infinite feel to it.
Okay, so in some sense you are saying that either at the state of the art or in a fundamental way, the bits that are stored in the wave function itself are not accessible.
They are not accessible, yeah. When you build a quantum computer, you actually use this feature that you can have things be in two places at once. So you use this wave, you superpose many, many waves, but the actual bits that would be required to describe the full wave function are not actually accessible. That's right.
Okay, so but the power of
Can I ask a question about this question?
we can't say no to our director.
In a way that is open or not?
Well, you are the director of the department, so it's going to be open anyway.
A dialogue. No, I was puzzled by the idea that the reality is digital or not, in my background as an engineer, as information engineer, the digitalization comes also with describing the difference between the noise and the information, and the role of noise is very fundamental in information theory, because the idea is that in principle knowledge of physics could be described by continuous quantities, but the fact that there is some noise that make this information or distinguishing the two continuous states impossible make very important to produce a model in which the reality has to become digital, because and so what is the role of the noise in the model that you are proposing here?
Yeah, that's a really good question, and actually I'm also a professor of engineering. So I mean, and people in engineering know that there are three things that limit information. There's the power, so it's the amount of energy you put into registering something. There's the bandwidth of the, how rapidly a signal can vary, and then there's the signal to noise ratio. So the power in the signal versus the power in the noise. Now classically these are independent of each other. So in a classical mechanics it would be possible to have a signal that varies extremely rapidly without adding extra energy, and also classically in principle you can reduce the amount of noise down to zero. But quantum mechanically these quantities are not independent of each other, and in fact if you have a finite amount of energy and a finite amount of volume, then you only have a finite amount of information. And one way to think of this is that in quantum mechanics is famously probabilistic. If I take an electron that's over in the superposition of two places at once and I measure to say is it 0 or 1, half the time it will show up being 0, half the time it will show up being 1. So quantum mechanics has an intrinsic form of noise, which is often called quantum noise, built in. And so this intrinsic form of noise in quantum mechanics then makes the actual amount of information in a quantum mechanical system finite. So that's a nice, the signal to noise kind of argument where the noise is supplied by quantum argument is a nice way of understanding why nature is digital and why the amounts of information are finite.
So this is a very, I think, far-reaching subject, because in some sense it underlies a slow but inevitable switch, even in the mathematics that is needed in our fields from continuous to discrete. Not that continuous will be abandoned, but so it will have implication even in education and so forth. But since we have a limited time, I will ask a different question. Again, I think something that might be important to realize is that the quantum revolution, already in physics it happened in the 20s, but the part that is relevant to information engineering is more recent, is not just that there is the promise to get faster machines, faster algorithms, but it really can completely impact the view of the world. In this direction, there is a line of work that Seth has been pursuing. I don't think he has made any reference during the talk, but I like to bring it up. And starting with something that is more close to my line of research, which is parallel and high-performance computing, we have discovered, even without being so close to physics as to look at electrons and atoms, that in computation the major cost does not come from processing the information, but it comes from moving the information within the system, whether we move it between the processor and the memory, or in a parallel distributed system, we move it across different processing agents. And you can prove some mathematical results, like if you want to compute a Fourier transform in the limit when the number of points goes to infinity, practically the effort to compute the transform it can be partitioned in processing and communication. The processing part fraction goes to 0, communication goes to 1. And one of the major efforts in making a computation efficient is related to mapping the computation into the physical system so that operations happen in space and time in an appropriate way. For example, in the memory hierarchy, two operations, one producing a value and the other using the same value, should be as close as possible in time, and in the space distribution as close as possible in space. So embedding the logical structure of the computation in the physical structure, in the structure of the physical space-time, is a critical thing. So I was very interested in reading about Seth's work, where he says, well, the universe can be viewed as a big computer where we have a logical structure. The logical structure and causal structure are, to a large extent, governed by the part of physics that we know of, the standard model of physics, the quantum electrodynamics and quantum chromodynamics. But when we think about embedding this computation in space, then the metric structure of the space, as described by Einstein's general relativity, comes out almost automatically. I might be misrepresenting the situation because I'm not an expert, and therefore Seth has proposed what we could call a fourth road to the theory of quantum gravity, based on the approach that the universe is a quantum computer. Fourth rod because there were three. The three rods were so baptized by Lee Smolin in a book, Three Rods to Quantum Gravity, and our string theory, quantum loop theory, and twistors. And we know that unifying quantum gravity with the quantum field theory is the holy grail of physics today. So I would really like to hear from Seth what is the promise of this of his approach, and in which way, in which direction his approach has given something more than the previous three rods.
Well, that is a very good question, and of course, quantizing gravity is hard. People started, as soon as quantum mechanics came out, using it to try to quantize Newtonian gravity. And when Einstein came up with his theory of general relativity 100 years ago, because this was the 100th year of centenary of Einstein's theory of general relativity, people started almost right away trying to quantize, make a quantum theory of general relativity, and they started failing right away. So several of my friends and I decided that we would put together a conference this year called 100 Years of Failing to Quantize Gravity. And this would be a fun conference because, first of all, we could admit to what went wrong. And then there are some people, actually from the string theory community, who believe they can quantize gravity, so they wouldn't come. So it would be a great conference all around. So it's very hard to quantize gravity and to make a quantum theory of gravity. The general relativity and quantum mechanics don't fit very well together. And I don't claim that this approach of thinking of quantizing gravity in terms of quantum mechanics and quantum information has succeeded in doing it. However, I think there are some contributions that not just I, but many other people who are working on this field have made. The first one is that when you're making a quantum mechanical theory of something, it's very important to figure out what are the observables, what things can be observed in the system. For people who work in quantum mechanics, particularly in things like high energy physics, if you try to make a quantum theory of something and you don't identify to begin with what you observe, then you're in trouble. And many of the problems in quantizing gravity can be traced to the fact that the central object in Einstein's theory, which is the metric, which tells how far apart things are in space and time, is not observable. So it's not an observable quantity. People can ascribe many possible metrics to system depending on how they choose to embed events in space and time. And this causes all kinds of problems. So one contribution that we did make was to say, well, let's look at what is actually observed in space and time. A good way of thinking about space and time observables is the global positioning system. You know that you have satellites that are going through space, they're sending out signals. The signals say when they've departed from a satellite, then you can record when they arrive, on your smartphone or at another satellite. And then you can build up a picture of the geometry of space and time from these signals. By the way, who invented GPS? This is a question for the audience. The global positioning system. Well, as an engineering system, actually with satellites, it was made by DARPA or ARPA in the 1970s, I guess it was conceived of and then put into practice. But the actual invention, the notion that we could tell where things are by having satellites sending signals to each other, was invented by Einstein. Because Einstein, in his presentation of general relativity, he discussed what is observable, and he did two models of observation. One is that you had a meter stick that allowed you to tell how far apart things were. This depends upon the material properties of the atoms. The second one is, he said, imagine a bunch of clocks which are falling inertially through space, for instance on satellites, and they're sending signals back and forth. About 15 years ago, my colleagues and I, this is actually with Vittorio Giovanetti and Lorenzo Maccone, who are now professors, finally managed to come back to Italy to become professors here. Some people here know about this problem. We decided to quantize GPS. So we made a fully quantum mechanical theory of all the atomic clocks that go into GPS, a fully quantum mechanical theory of the signals, and we derived the quantum limits to measuring space-time geometry. And this, I think, is very helpful because, first of all, it's actually helpful from a very practical standpoint because, in fact, these actual models that we make are being used by people like Dave Weinland at NIST to make more accurate atomic clocks, and are being contemplated by the people who make GPS for make signal processing, time of arrival and departure measurements more accurate. So it actually has a kind of a practical purpose, but it also provides insight into what's going on in the quantization of general relativity and to looking at how the universe as a whole is processing information. For instance, one of the insights that came out of this was that you mentioned that I calculated the number of bits that are there in the universe. It's something like 10 to the 90 bits in ordinary matter, and maybe 10 to the 120 bits if you take into account all possible degrees of freedom. And the number of bit flips that can have taken place, the number of events since the beginning of the universe, is also about 10 to the 120. And though this is a large number, it's not that large a number. I can think of much bigger numbers. And indeed, it's a much smaller number. If you asked a quantum field theorist or a string theorist how many events were taking place, they would guess a much larger number.
Or even how many variants of string theory there are.
Ah, yes, that's right. That's right. It's roughly about the same number of variants of string theory, which is maybe is a coincidence or maybe not.
One per atom.
One per atom, one per elementary particle. So, yeah, I think this is a potentially very fruitful approach, and actually, in fact, now the string theory community, though for many decades they'd been telling me that they had quantized gravity already, because they couldn't calculate anything, I couldn't tell what they were quantizing. So now they actually seem to be adopting this approach based on quantum information. So I think maybe that's a good sign, or maybe it's a bad sign, I don't know.
Okay, let's go to something more technological, although if I were to follow my heart, I will stay on these fundamental issues because I think they eventually give us a light even for where technological research should go. But we know that the promise, for example, for computing, the promise of the quantum approach requires a combined success. On the one hand, we have to have quantum machines, reliable, large enough quantum machines, and on the other hand, we have to have good quantum algorithms, because the ability of a quantum system essentially to simultaneously process, a quantum Boolean circuit can simultaneously process, so to speak, all the 2 to the n inputs, but it is then very hard from the output, the qubit, to know what the function, properties of that function. So only for certain problems have we, up to this point, found ways to take advantage of this huge parallelism that exists at the, if you wish, at the wave function level, but then we have to measure. And as Seth was telling us, once we try to measure to get the information, we have a sort of a collapse. So I'd like to get your point of view on two things. One is quantum machines. In particular, there's been a lot of publicity about the D-wave machine. Google got one, and Lockheed Martin got another one, and as my old friend Umesh Vasirani at University of Berkeley, an expert in quantum computing, claims that such machine cannot be in a few years faster than a cell phone. So there has been a big debate, even to the question of whether we should consider the D-Wave a real quantum computer or not. And I know you have worked a lot on the foundation of adiabatic computing, which is the approach they take. So what's your take on the D-Wave?
That's a good question. So, well, let me just say, first, this is a wonderful era for quantum technologies. I was mentioning these quantum technologies having to do with measurement and GPS. So, for example, the world's most precise quantum clock, which was cited in Dave Wineland's Nobel Prize, is his quantum logic quantum clock. And so he uses methods from quantum computing to make an optical frequency atomic clock, which is the world's most precise device. Similarly, in metrology and communications, quantum mechanics is playing a very important role. And in fact, in supercomputing, as the scale of computers, of the components of computers, presses down towards this quantum scale, quantum mechanics will inevitably have to be taken into account. So we're in a very fine era of using quantum technologies. Now, to talk about D-Wave, it's important at the very beginning to say that what D-Wave is building, so D-Wave, for people who don't know about this, is a company in Vancouver that is building a quantum device, a special purpose quantum information processing device, which is called a quantum annealer. And it tries to find the answer to hard problems by mapping their solutions into a physical system and by trying to find the lowest energy state or ground state of this physical system using a quantum mechanical means. calling it quantum annealing for people who are in computing and optimization. It's a quantum mechanical analog of the classical process of simulated annealing, where you map the answer to a hard problem into a bunch of physical constraints or energetic constraints. You try to find the lowest energy state of a system by effectively cooling it down. The first thing is that a quantum annealer is not a general purpose quantum computer, so it can't do all the things that a general purpose quantum computer can do. For example, factor numbers and break codes, perform quantum simulations, etc. But it is potentially an interesting device. But it is not a general purpose quantum computer. It's a device that's using quantum mechanics to try to find the answer to hard problems. The second thing to remember about this is that nobody knows whether it can solve hard problems or not. So it does already solve hard problems. So this D-Wave device, it consists of their new devices are several thousand quantum bits. You can solve a problem, a hard constraint problem over several thousand bits. Actually, such problems, because these problems can be NP hard or NP complete, solving it over 1,000 bits is pretty good because it's combinatorially difficult. So it is working. It is solving problems. The debate is over whether it will be able to solve problems faster than classical devices, and there nobody knows the answer. People like Umesh say it won't be able to do it. Other people say it will be able to do it, and I say I don't know whether it will be able to do it or not. I think we have to wait and see. My involvement with D-Wave stems from the beginning because in 2002, my graduate student Bill Kaminsky and I proposed building a quantum annealer, a device like this device. They didn't exist at this point, using superconducting. I guess the exact description of what we proposed, we said, let's use superconducting flux qubits with tunable inductive couplings using a tri-layer niobium manufacturing process. And then we didn't patent this because we did a few calculations and we said, oh, it's not going to work. So then D-Wave spent $150 million building a quantum annealer based on superconducting flux qubits with tunable inductive couplings on a tri-layer niobium process. And we felt pretty stupid. By the way, my advice for this is patent everything, even if you're sure it's not going to work.
Especially if you're sure.
Right, especially if you think it's not going to work, because then somebody just might go ahead and build it anyway. So you don't know. And ironically, I mean, indeed, this D-Wave device, even though it doesn't work in the way it was supposed to originally, it still works. So I think what's going to happen with D-Wave is, I should say that I've been working with D-Wave and consulting with them because I know a lot about how their device works to try to figure out what's going on with their device and what you might be able to do with it. It does behave in a very quantum mechanical fashion. So at bottom, it's exhibiting all kinds of quantum effects like entanglement, for instance. It is solving problems that it would seem would be hard for classical computers to solve, but easier for quantum annealers to solve. So it's behaving the way you would expect. And really the open question is, and it is operating in a quantum mechanical fashion. So the question is, can it solve hard problems that couldn't be solved classically? And I think the answer there is, we'll find out over the next 5 or 10 years if that's so.
Okay, thanks. I have many other questions, but I also see Paolo that rightly reminds me that we should probably open the discussion to the public.
Yes.
Not just the director.
Yeah.
So.
Okay. So we would like now to see if there are questions on also topics that are addressing different aspects of these coming from the public.
Touch only briefly about the biological realm. What about the coherence, such things?
Yeah, so the question is, what about quantum coherence in biological systems? Yeah, that is a really fascinating topic. I got involved in this topic in 2007. I got up one morning and I looked at the New York Times, and there was an article in the New York Times that said, purple sulfur bacteria are performing quantum computations. And I took this article to our quantum computing group meeting, and we read it, and we all laughed and laughed and laughed. This seemed the silliest thing that one could possibly imagine. But because it was based on an experiment done by a very well-known researcher and group at Berkeley, Graham Fleming's group, and a very beautiful 4-wave mixing femtosecond spectroscopy experiment. We felt we had to go check out this claim. So Alain Asper-Guzik, who's a professor of chemistry at Harvard, and I went to go look in detail at these claims. And we found out that right away that they were wrong, at least the way they'd phrased this, that they claimed that, oh, maybe these bacteria are using quantum coherence to do a quantum algorithm to search for, well, in photosynthesis, light comes in from the sun, a particle of light, a photon comes in. It's absorbed by a chromophore, a light-carrying molecule. It creates an exciton, a bound electron-hole pair, a so-called Frankel exciton. This is a particle, as its name suggests, it's a particle of energy, a particle of excitation. And then this exciton hops from chromophore molecule to chromophore molecule through a large photocomplex, which may contain hundreds to hundreds of thousands of molecules, till it gets to a point, the reaction center, where this energy can be taken advantage of. The electron and hole and the exciton are split. The energy can be turned into chemical energy. And that's how photosynthesis works. So what the experimental evidence was that after the light comes in from the sun and creates this exciton, that this exciton, because it's a quantum particle, even though it's just some excitation of a molecule, that this exciton, instead of just hopping in some classical way through the photocomplex, it has a wave associated, and it takes all possible paths simultaneously. And it's the quantum interference between these paths that allows this process to be efficient. And actually that is true. And in fact, what's happening is that this exciton is taking what's called a quantum walk, which is a way of moving from place to another that uses quantum coherence, the wave-like nature of quantum mechanics, to get from one place to another faster. And what the experimental evidence now shows very strongly that this is the case. That is that quantum coherence is playing a very important role in photosynthesis, in helping this energy transport process in the photoantenna to be almost 100% efficient. And my colleagues and I have had a lot of fun taking models that we developed for quantum computing and applying it to this very rich phenomenological field and working with experimentalists to go and investigate the ways in which quantum coherence plays a role. So in photosynthesis, quantum coherence plays a very important role. In retrospect, it's not that strange. The kind of time scales involved, the initial absorption takes around tens of femtoseconds. Then this hopping process takes hundreds of femtoseconds to a few picoseconds. The coherence times are on the order of tens of picoseconds. So quantum coherence can play a role. And one thing that's great about biological systems is if some physical effect can play a role in making something like energy transport more efficient, then they're going to take advantage of it. And the way I describe this, these green sulfur bacteria, many of them live deep under the ocean surface, kilometers beneath the ocean surface, at hot water vents, where the only thing that they can photosynthesize, there's no light at all from the sun, they're photosynthesizing black body radiation from the hot sulfur vent. So if you're a bacterium and it's like an hour has passed, it's like, oh, finally I caught a photon, now I have an exciton, right? Now the children can eat. Oh my God, I dropped the exciton. Then it's like, oh, you fool, you dropped the exciton, the children will starve. So just for marital relations between purple-green bacteria, it's very, very important that this be an efficient process. So if quantum mechanics can help, the family lives of green bacteria, then in the end you'll find out it will, and that's what happened. So now there are other claims for use of quantum mechanics and quantum coherence in biological systems. The one which is not correct and is outright wrong is in the brain. There's this Penrose-Hameroff idea that somehow quantum coherence is playing a role in the thought process. And actually, Penrose is a brilliant mathematician, and he did propose something which was very scientific in the sense that it's falsifiable. And actually, a very simple calculation will tell you that the time scales and energy scales involved in neural processes are far, far too slow and the energy scales are far too great for quantum coherence to play a role in actual neural thought processes. So it's a falsifiable theory. It was falsified immediately upon being put out. The only problem is that Penrose and Hameroff haven't realized that it's been falsified. But there's no quantum coherence playing a role. But then there are a whole bunch of other possible places, such as, for instance, in receptor dynamics in cells, or actually in synapses. You get in receptor dynamics in synapses. In molecular reconfiguration, quantum coherence could easily be playing an important role there. And I think there's a lot of work to be done to try to tease out the role of quantum coherence in living systems, because, as I said before, if quantum coherence can make things work better, then you would expect living systems to have found ways to use it. And in the case of photosynthesis, they have.
Other questions?
When I have a very simple system, I can tell I have a 1 and a null. But where is the information about what system do I have?
This is now we were having a good conversation about philosophy last night and metaphysics. Yes. So okay. So actually, let's take an example. So let's take the example of an atom, right? And we call a hydrogen atom, the electron in the ground state of the hydrogen atom we call that null or 0. The electron in the first excited state, we call that 1. And this is a quantum mechanical system. There are two states that we're looking at. We focus our attention on two states. But the system itself is a hydrogen atom. Now, okay, so what makes it a hydrogen atom? This is of course, very interesting. This, of course, also comes from quantum mechanics, right? Quantum mechanics implies that because of the four fundamental forces of nature, in particular because of the strong force and the electromagnetic force, these play the most important role, you can only put together elementary particles to make, protons and neutrons and nuclei in a particular way. So, a proton is maybe the simplest form of stable collection of quarks, and then you can only put electrons together with nuclei in particular forms. And the simplest form this could take is a hydrogen atom. And then quantum mechanics describes, how a hydrogen atom can form and, what different possible states it can have. Indeed, this was Niels Bohr's first contribution to use quantum mechanics back at 100 years ago to show how hydrogen atoms could be made. So if you look at the level of what makes a system, then what makes a system is also quantum mechanics and information describing the particular form. The information describes the form that the matter and energy can take, that in this case it takes the form of a hydrogen atom. And when you take a quantum bit and you move it from one state to another, you transform that information. Now it's I've said it so many times it's not making sense to me anymore. But you change that information. So quantum mechanics also specifies what systems can exist.
Well, could we say that in some sense the atom itself is a state of the underlying field?
Absolutely, yeah. Yeah, I mean, electrons and protons are states of the underlying quantum fields. You put them together, then the atom itself is a more complex system, which is a state of the underlying quantum fields. And it does, the fact that it's a hydrogen atom rather than a helium atom registers information as well.
Thanks for your talk. I study biological evolution, and my curiosity is related to two questions. The first one, is your way to see evolution, the origin of life, the evolution of life as an information process, just a very fascinating metaphorical description of the process, or is it able to produce specific new hypotheses about evolution? For example, the role of quantum coherence, or maybe in genetic mutation, very teeny processes, because evolution is a very macroscopic process. So it's just a way to describe in a different way the process, or do you think it has an heuristic power to produce new hypotheses in order to better understand evolution, biological evolution?
Yeah, that's a fascinating question. I mean, of course, at the genetic level, natural selection and evolution is about information. It's about changes in genetic information. But the information that's in the genome is at, as you say, it's at a very high level. It's it's a result of billions of years of evolution, and it's a very sophisticated. It's embedded in cells, which are an extremely sophisticated mechanism to process the information that's in the genome in a very complicated fashion. So it's certainly the case right now that that natural selection is about information and metabolism, etc. So, but a really interesting and question to which I don't know the answer, but I have a hope that the kinds of processes that I've been describing in terms of physics and information could play a role, as in the description of prebiotic evolution, if you want. How did life come about in the first place? How did we get to this situation where we have things, I won't call them organisms because maybe they're not organisms yet, that reproduce and reproduce with variation, and that take advantage of the free energy in their environment to do that. Now those questions are questions about information. Free energy is energy that comes with information attached, and in order to take advantage of the free energy, you have to decode it. So you have to have the ability to take advantage or decode this information. I think that one can talk about that kind of process even before we have things like DNA or RNA or whatever things came before DNA and RNA. We can talk about this kind of process in terms of information processing in the way that I described, and maybe make some progress for looking at how life might have originated in the first place. But I'm not making any promises.
So, from what I understand is that most of the work for computation theory and implementation for quantum information is done is theoretical now. So, for a computer scientist standpoint, how much there is a room for improvement of optimization and algorithms, or are we just waiting for an implementation, and the theoretical part of that is figure out? So I don't know if you understand.
No, I understand that perfectly. That's an excellent question. So the status for general purpose quantum computers that you could run any quantum algorithm on is that right now there are quantum computers that have 20 or 30 quantum bits, and that's just at the threshold where you could still simulate what they're doing classically on a huge classical digital supercomputer. But because of advances in quantum technologies, over the next 5 to 10 years, we're very likely to have quantum computers that have between 50 to 100 to 1,000 quantum bits that can perform tens of thousands of coherent operations. And these are devices where you couldn't simulate them classically, and that they could do things that classical computers couldn't. So in this context, given what's about to happen technologically, and by the way, I'm reluctant to make technological predictions because they're almost always wrong. But and for many decades, I've been not making predictions about when we'd have these advances in quantum computers. But right now, there are advances in superconducting circuits and in ion traps and laser physics that mean, and atom optical physics that mean it's very likely we're going to have these larger scale, kind of mid-scale quantum computers. In this context, it's extremely important to develop actual new algorithms for quantum computers. Quantum computers, there are not many algorithms for them. I mean, there's Shor's algorithm, which allows you to factor numbers and to break codes. Then if you look at subroutines, there's things like the quantum Fourier transform. So the classical fast Fourier transform over n data points, the discrete Fourier transform takes time n log n. And the quantum Fourier transform takes time log n squared, so it's exponentially faster than the classical one. This quantum Fourier transform is at the basis for many quantum algorithms. Maybe I'll just make a list of what we have, because we don't have that much, okay? And maybe it's not that surprising because, there's not a lot of room between NP-complete problems, and I sense that you're a computer scientist, right? So I'm allowed to talk computer scientist speak, right? There's not a lot of room between NP-complete problems and problems that could be solved in polynomial time with a small polynomial. So, so the ones that are faster, so Fourier transform goes from n log n classical to log n squared quantum mechanical. That's exponentially faster. finding eigenvectors and eigenvalues. So if you want to find the eigenvectors and eigenvalues of a sparse n by n or a sparse or low rank n by n matrix, classically, it's the best you can do is basically n squared via for a sparse matrix, or n cubed for a low rank matrix, and quantum mechanically it goes as log n squared again. So it's exponentially faster. In fact, it's much faster because it's actually going from something like n squared or n cubed to log n squared. So that's actually very powerful because things like principal component analysis get much faster. Sorry for people, if this sounds like I'm just going to answer. I'm just going to tell it to other people if you want to find out what all this. Most people here, I'm sure, know what I'm talking about. But if you don't, that doesn't matter.
You cannot say that.
No, but we can talk. If you don't, we can talk about it afterwards. So, finding eigenvectors and eigenvalues principal component analysis goes from n squared to log n squared. Matrix inversion, solving sets of linear equations. Inverting an n by n sparse or low rank matrix takes time n log n by conjugate gradient descent on a classical computer, takes time log n cubed on a quantum computer. So again, it's exponentially faster. So actually, one of the interesting things is that if you look at the kind of things quantum computers can do, there are a lot of the kind of very, very common subroutines that actually, it's what's in MATLAB, the BLAS, the basic linear algebra subroutines, as they're called. Many of these become exponentially faster on a quantum computer. And so there's a lot of room for constructing algorithms that are made up out of these basic linear algebra subroutines. They would be exponentially faster on a quantum computer. And then this would be very useful in the kind of small, medium-sized quantum computers that are showing up. So, I mean, the work we've been doing about machine learning, quantum machine learning, showing that there are a lot of algorithms, like, for instance, principal component analysis is exponentially faster on a quantum computer. Support vector machines and cluster analysis is exponentially faster. We actually have a bunch of financial analysis algorithms, so portfolio management and option pricing. And here our goal is we realized that during the last financial crisis, 2007, 2008, that, I mean, it's not, this is kind of an open secret, but if you note what caused it, well, what caused it, of course, was, highly over-leveraged investment banks and, foolish investments in real estate, and the whole system was out of whack. But we know that also that there are tens of thousands of people with PhDs in physics working for financial firms, because if you're a financial firm and you want someone who is really very adept at mathematics, has their feet on the ground in terms of the empirical relationship between the real world and mathematical models, can evaluate very well the risks of different mathematical models, then you should hire an unemployed string theorist, because they're the people who really know about this. Sorry.
He's employed anyway.
He's employed, right? He's an employed string theorist.
He doesn't fall in your category.
Exactly, that's right. For good reason you're employed too. Yeah. So indeed, we felt that in quantum information, we hadn't participated in this, and we really, if the physicists previously could make algorithms that took $20 trillion out of the world economy, we could actually make quantum algorithms that would destroy the entire thing. So, but there are lots of possibilities in terms of algorithm construction. In some sense, this is the most pressing need in quantum information theory right now, is to construct new and better algorithms, because the devices are going to be there. So we need more algorithms.
Could we claim from a physical point of view that information is a property of the universe, just like mass? Or is it more a mathematical construct?
Yeah, I think that we should claim that. I mean, in fact, as I mentioned earlier, that if you look at the formulas for information theory, they really were developed in the 19th century to say what is the quantity that we call entropy. So, already the first step along this process was to show that heat, the physical quantity heat, is energy, and it's the kinetic energy of the atoms and molecules that are bouncing off of each other. Then what is this quantity entropy? So entropy is actually information. It's the information required to describe how the atoms and molecules are bouncing off of each other. So I think it's fair to say that it's a fundamental physical quantity. I mean, of course, it has just in the same way that kinetic energy is an abstract mathematical quantity, then also entropy or information as an abstract mathematical quantity, but they're mathematical quantities that have a very direct and important physical interpretation. And in some sense, this has been known for 150 years. So I think there's no, one should just accept this. It's been known, it's a very fundamental part of physics.
Since before you talk about the Penrose model, I would like to ask if you have some specific comment about his last claims of a couple of years ago, when there was some experiments by a Japanese group about some vibrational states of microtubes, and according to Penrose, this would be some evidence for his model.
Oh yeah, I can comment about that. Yeah. It's not evidence for his model. No. No. Let me be more specific. So this Penrose-Hameroff model. So I mean, as I said, it's a good model and a scientific model in the sense that it's concrete enough to be falsifiable. So I mean, it looks at the assembly and disassembly of microtubules, which are a very important part of kind of moving things around within cells and like forcing conformational changes in cells. Moreover, this assembly and disassembly of microtubules has an explicit computational function in the sense that they're made in a brick-like structure, and you can have different kinds of bricks, say two different kinds of molecules, and according to which molecules come down, then they can change their conformation and change direction or branch. So there actually is a very explicit computational-like structure in microtubule formation. I mean, this is called a cellular automaton, and computationally it's called a cellular automaton-like structure. And so Penrose and Hameroff realized, hey, this is like computation. So that's fine. It is like computation. You can think of it as computation. And information processing in microtubules is very important for the way cells work. Moreover, because you're actually having molecules that are binding to different things, then you're going to have all kinds of vibrational modes. And at the level of individual molecules and actually binding events, it will be behaving in a quantum mechanical way. And you'll see that the quantum mechanics plays a role in this, because quantum mechanics governs chemistry. It governs how chemical reactions take place, and quantum coherence is actually very important in chemical reactions. So all that is fine, right? And the problem is that the act of one of these building blocks coming on and adding itself onto a microtubule is a highly dissipative event. You dissipate, electron volts worth of energy gets turned into heat. And what that means is you cannot have a quantum superposition of having this building block and another building block in the same place, because it decohered over the course of whatever time scale it took for this to bind and the heat to dissipate. So it's just not quantum coherent. And it's very easy to show that. My colleague Max Tegmark, for the benefit of the community, wrote a paper showing this is true, but everybody knew that it was true. It's obviously true. So there's no quantum coherence in the actual putting together of these microtubules over larger scales. There's quantum coherence at the scale of individual binding events and at the role of vibrational modes, but there's no quantum coherence in creating a quantum superposition of these different structures. So, and that's why the Penrose-Hameroff model is wrong, and has been shown to be wrong, and was shown to be wrong, almost 20 years ago. It's just that Penrose, he's a mathematician and not a scientist, so he doesn't realize it's been falsified. So it's okay. I mean, I think I've had some wonderful conversations with Penrose, and he's a wonderful person and a truly brilliant mathematician, and he makes models that are scientific in the sense that they're falsifiable. But sometimes he holds on to them for a little too long, that's all. We all do that in our lives, hold on to things too long.
And then let's thanks again Professor Lloyd for his talk and all the answer he gave.
Thank you,
and to
Gianfranco as well. Thank you.
Yeah.